All right, let's talk about organic chemistry. You hear these words all the time, methane, propane, and octane, but what do they actually mean? It sounds like this crazy secret language, right? Well, guess what? It's actually built on a really simple, kind of beautiful system. And today, we're going to crack that code together.
So, to get us started, here's a weird question for you. Why on earth is the octane in gasoline named after an octopus? I mean, that sounds completely random, right? Just hang on, because the answer is actually the key to this whole thing. And it's way simpler than you think.
Okay, so why do we even need a system like this? Well, it's because of the sheer numbers. We're talking about millions of different hydrocarbon compounds. Millions. Can you imagine trying to keep track of all that without some kind of logical naming system? It would be absolute total chaos.
But thankfully, there is a code. It's really more like a language. And the cool part is, once you learn just a few basic rules, a little bit of grammar, you can start reading these molecule names like you've been doing it your whole life. So let's dive in. Let's learn the language.
All right, Section 1. Just like any language, we got to start with the basic vocabulary, right? For hydrocarbons, that vocabulary comes in the form of prefixes. These are just little bits at the beginning of the word, and they tell you the most important piece of information, exactly how many carbon atoms are in the molecule.
And here they are, these 10 little prefixes. They're the foundation for pretty much everything. So meth is 1 carbon, F is 2, prop is 3, but is 4. And then it gets easier. Pent, hex, hept. You've seen these before, right? Like in pentagon, hexagon, or decade. It's all coming from the same Greek and Latin roots.
And hey, look at number 8, oct. This brings us right back to our octopus question. So the prefix oct just means 8. That's it. An octopus has 8 arms, an octagon has 8 sides, and a molecule of octane, well, it has a chain of 8 carbon atoms. See? Simple as that. Mystery solved.
Okay, Section 2. So we've got our vocabulary, the prefixes that tell us how many carbons. But that's only half the story. Now we need a little grammar. And that's where the suffix, the ending of the word, comes into play. The suffix tells us how all those carbon atoms are actually holding hands.
And really, there are just 3 main ones you gotta know. Ein, and ein. It's pretty straightforward. If the name ends in ein, that means all the carbons are connected with simple, single bonds. If it ends in ein, you've got at least 1 double bond in there somewhere. And if it ends in ein, you guessed it, there's a triple bond.
Let's break that down a bit. First up, the alkanes. They end in ane, and they are the simplest of the bunch. You can literally just picture a chain of carbon atoms all holding hands with a single bond. Nice and simple.
Next up, we have alkenes. That "ene" ending is your clue that things are getting a little more interesting. Somewhere in that chain, 2 of the carbons decided to form a much stronger double bond. And that one little change, it affects the whole molecule shape and how it behaves.
And finally, you've got your alkynes. That "-ine" at the end tells you there's an even stronger connection happening, a triple bond between 2 of the carbons. Now, these aren't as common, but they're a totally essential part of this whole naming language. All right, Section 3. We have our prefixes, which tell us the number of carbons. And we have our suffixes, which tell us the type of bond. You know what that means, right? It's time for the magic part. Let's stick them together and build some actual molecule names.
This is it. This is the secret formula. It's just prefix for the carbon count plus the suffix for the bond type. And that equals the name of your hydrocarbon. Seriously, that's the whole core of the system right there.
Let's put this into practice. Okay, say we have a molecule with 3 carbons. We know from our list the prefix for 3 is prop. Now, if all the bonds are single, we just add ane, and boom, you get propane. Yep, the stuff in your barbecue grill. If there's a double bond in there, it becomes propene. And with a triple bond, propyne. See? 1 prefix, 3 different endings, 3 totally different molecules, all from the same super simple rule.
Okay, so Section 4. This is cool. We can now read the name, but what about when you see the chemical formula written out, like C3H8? We get the C3 part, that comes from prop, but where in the world does the H8 come from? It's not just a random number. There's actually some really simple math behind it.
I mean, that's the next question you'd ask, isn't it? How does a molecule just know how many hydrogen atoms it needs? Well, the answer goes right back to what we just learned. It all depends on the type of bond. And we know how to spot that by looking at the suffix.
Check this out. There's a super easy formula for this. If your molecule is an ane with single bonds, you just double the number of carbons and add 2.
Simple. If it's an ene with a double bond, you just double the carbons, and for an yne with a triple bond, you double the carbons and subtract 2. It's like a little cheat code, +2, 0, -2.
Let's go back to our 3-carbon example, the prop family. For propane, that's an ane, right? So we take our 3 carbons, double it to get 6, and add 2, which gives us 8 hydrogens, C3H8. Perfect. For propene, the ene, we just double the 3 carbons and we get 6 hydrogens, C3H6. And for propyne, the yne, we double the 3 carbons and subtract 2, giving us 4 hydrogens, C3H4. Look at that. The math just works every single time.
So let's just wrap this all up real quick. What did we figure out? A hydrocarbon's name is just a 2-part code. That's it. The start of the word, the prefix, tells you the carbon count. The end of the word, the suffix, tells you the bond type. And using just those 2 clues, you can even figure out the exact chemical formula.
Pretty cool, huh?
And there you have it. Just like that, something that sounded like a totally foreign, secret language just a few minutes ago is now something you can actually read and understand. You've basically just learned the fundamental grammar of organic chemistry. That's a huge deal. It's a skill that lets you unlock the secrets of millions of different molecules.
So, from now on, when you're at the gas station and you see octane, or you hear someone talk about butane lighters, you'll know exactly what they're talking about. It kind of makes you think, doesn't it? Now that you see how this complex world of molecules is really just based on a few simple rules, what other big, complicated things in the world are just like that, just waiting for us to figure out their language?